These are all the questions that are possible from module 5 of IoT. So we'll start with the first one. So what is Arduino? Basically, Arduino is an open source advancement prototyping platform which depends on simple utilization of equipment and programming. Arduino, we have a board which provides a platform to program and then allow the data and data exchange to happen on a board. So it's basically a microcontroller. So the instructions to the microcontroller are given using the Arduino programming. Arduino programming is the type of programming which you use to write into the microcontroller board. So the Arduino software, that is you have your Arduino software for programming in Arduino. The Arduino is a small computer that can program to read the information of the world around you and send commands outside of the world. Arduino is a tiny computer, so this microcontroller works as a tiny computer that can be connected to electrical circuits. The brain of the board, that is our 80 mega 328P chip, that is, you have a microcontroller which acts as a brain of your Arduino device. This, what happens with this brain is it stores the programming, like your brain stores information, and will tell your Arduino what to do. So for basic information, there are a lot of versions of Arduino board which are being released, but here in IoT we study only about Arduino Uno learning board. So in this we see the diagram of the Arduino Uno learning board. What are the components are? You have a power jack for which your power can be supplied. You have a normal jack, then you have a reset button, and then here you have your digital inputs which can be given, and then here you have a power LED button that is either to on and off, and then you have to write, to symbolize this is an Arduino Uno board, you have to write this infinity sign with a minus and plus mark inside. Here you have power buttons, and then here you have your analog inputs which can be given. So you have one power pins over here, you have analog pins over here, and then you have a microcontroller. These are the components of your Arduino board. So here you write your microcontroller, that is 80 mega 328P is your Arduino brain. So your like first we discussed, right, the Arduino brain, that you have to remember that it is 80 mega 328P, and then you have digital pins, that is 0 to 13. These are your digital pins which are here. And then for your input and output, you need to supply it with power, right? So what happens is your high voltage can be up to 5 volts, and then your low can be 0 volts. Then you have your PWM pins. These are the digital pins from 0 to these are your digital pins that are 11, 10, 9, 6, 5 and 3. The PWM stands for pulse width modulation. You have a TX and RX pin. When you check your diagram, you know that there is, if you see properly here, you have a TX and RX pin. What this TX and RX pin is, it gives you digital pins, that is 0 and 1. Here T stands for transmit, and then R stands for receive. So what happens is this gives the transmission signal, that is over here, and then this gets the receiving signal over here. You have a power LED over here, right? So what happens is when you turn on, you get an indication of either having a green light or a red light, right? So this is the LED's function. So this is usually attached to the digital pin number 13. These TX and RX pins, they blink when the information is being sent between computer and the Arduino. So here what happens is, we've seen that we have analog pins over here. So these analog pins are labeled from 0 to 5, that is A0, A1, A2, A3, A4 and A5. These are mostly used to read analog sensors. And then the power pins, that is these pins. These are your power pins. They have 3.3 volt or 5 volt supply of power which is given to them. The pins are labeled as ground. There's a ground labeled pin over here. So it is written as G and D. So this symbolizes the grounding pin. Then you have the reset button of your program. This is used to run your Arduino, and it'll start from beginning. It'll start the whole programming from beginning. Then you have this jack. This is the USB jack, where you can you're connecting your computer using this USB jack from your Arduino board to your computer. Then you have a power jack which is connected to the component to make sure your power is there. So that this is either 0 volts or 5 volts which are being short. Structure says that it contains two parts. One is void setup and void loop. So void setup, what happens is you're giving so in setup what happens is you give them values, you declare the values, and you're allocating the values. So what happens is in setup you declare the values and by giving statements inside of it. So this enables your set pins for serial communication. And then you have void loop. So if you have any execution of block statements that you want to repeatedly perform, then you use this void loop and then you give them statements. This is your main structure of the Arduino programming. Then you have functions which has to be written. In this function you can see that type, your syntax will be type, function name, and then parameters. So if you are writing type, overloading, and parameters, that is a comma b. So while writing data types, your main part is you need to. So under data types, what happens is you have byte, int, long, and float, right? So you write your data type and then you write your variable name with a value which is assigned to it. So what happens is for everything it's the same. For byte it's byte, for int it's int, long, float and float. But for when it comes for arrays, you write int, that is your homogeneous data element types which will be present, and then you give your name to an array, and then you write box brackets, that is it's written over here. So you write your box brackets equal to, open your curly braces, and then write your values whichever needs to be present, and make sure all your values are homogeneous. That is if you are giving an int type, make sure everything is of the type int, and if you're giving float type, make sure everything is of the type float. So for your digital input output, there are the methods are classified as 4 parts. Okay, here we have pin mode, digital read pin, and then you have digital write pin, and then you're giving some examples. So what you're doing is you start off with a pin mode, that is you give your parameters are pin and mode. So first you give the so you write this pin mode in setup of. If you remember, the setup of function had statements that will help us to communicate with the board. So what happens here is you give the configuration pin to the respective input or output. The pins which we have is it can be used for both input and output. So you have to clearly define pin mode, that is your pin, comma pin number, that is your 7 or 8, and then input. This is given for input mode, and this is given for output mode, as both as one pin can perform both input and output function. Then you have digital read pin. So what you're doing is you're asking it to read the value if it's being high or low. If the value is you're reading the value and and you're giving the value over here. So you take you read the value, and then you decide whether it's a high voltage value or low value. So the value will be equal to the input pin. And then you have digital write pin comma value. So what you're doing is here you're giving the value to be written. So what you're giving is you give your pin volt and then you give high, or you give pin number and then you give low. So you write digital write off and then the pin's value. And then you will give you an example over here, that is you have int x that is connected to 13 pin. X is 13, p is 7. So your pin you connected push button to pin 7. Okay, so in this example you have a push button, and then you have x which is connected to pin 13. So you're storing the value val as 0, and then you're writing void setup, and then you open the bracket pin mode, then you're writing the pin mode, and then you put x is equal to output. Here what it means is you're setting the value of 13 to be the pin value 13 to be your output. And then you go to the loop. You're giving a void loop in the program. So what you're doing is you're upgrading the value of val. So val is equal to digital read of p. So whatever the value which the pin 7 gives us, you're reading that value, and then you're writing x as the value over there. So you're setting so what's happening here is first you're taking x as 13. So your 13th pin value is given. You're taking x as your 13th pin, and then you're making it as output value. Okay, and then what you're doing is next you're reading your digitally reading p. That is, your p value is given as 7. P is 7. So what you do is digital write. Now you're taking x and then you're writing the value of you're writing now you have p as 7. So now what you're doing in this part is you're making val as 7. So you're reading the value and then you're storing it in val. So now you're making x as now x's value becomes 7 because x is being upgraded to the next value. Now you have smart cities and connected cities. Now in this, your IoT strategy is for smart cities. Okay, so what you're doing here is you're managing a city that bears resemblance to manage a corporate enterprise. What you're doing is you're adding sensors to make sure the whole city functions in a more efficient and organized way, so that it has operational efficiencies. So using help of new tools. Okay, for cities, as just like businesses, digitalization and transformations are what we are putting on operations. And then you're using new ideas that emerge and bring different approaches to solving these things. So what you're doing is you have vertical IoT needs for smart cities. What are your vertical IoT needs? Now if you go see the related thing. So you have many different approaches to solve city management. Okay, so everyone has a different set of problems and you have different solutions which you can think of. So all those this typically start with the street level with sensors capturing data from parking space availability to water purity. So and then you have data analytics, which is used extensively to reduce crime or improve efficient traffic flow. The citizens can use tools to leverage their smart mobile devices, such as report problems and make recommendations for improvement. So and then you have enabled through connectivity. These smart solutions can have a transformative impact on quality of life. So what you're doing here is you're using smart structures, that is to whether to indicate you have a vacancy in parking space or anything like that. So you have parking systems in India where which shows the vacant parking spaces, and then it automatically times. Here what happens is your sensors are placed underground or near the parking spots to monitor the amount of time which has been your vehicle has been in the parking space, and then you are charged accordingly for the services they provide and safety measures that they ensure for your vehicle's parking. So these cities have the potential to claim 2/3 of the non-dense or IOE public sector values. So what happens here is you have smart buildings, you have gas monitoring systems, you have smart parking spaces, water management, and road pricing. So your road pricing has your lowest, that is your $18 million for cities, and then you have next is your water management by $39 billion. And then you have smart parking by $41 billion. And then you have your gas monitoring, that is your $69 billion. And then your smart buildings, that is when you walk in, your lights of your home automatically turn on, and if it detects that nobody is there in the room, your lights turn off. So all those are smart buildings. Your parking garages open doors automatically. When you walk into restaurants, when you walk into your restaurants, there are doors which open automatically by sensing the presence of a human body, right? So all those come under smart buildings. So for smart buildings, when you go down, So these are the use cases, and then you have smart buildings. Smart buildings have the potential to save, this saves, this is not your allocated money or fund, these numbers, these are the amounts which you can save by lowering the operational cost. So instead of keeping a door person to open the door every time they come in, so you're using smart sensors, and which are installed and opens door automatically. So $100 billion can be lowered as operational cost. And energy consumption can be reduced by heating and ventilation. You have your ACs which turn on only when there are it detects how many people are there and the heat, and then it manages temperature accordingly, right? So all those come under your smart buildings. You have financial gain which applies to city budgets when the city is being building a city is owned. However, the reduce so to you have to reduce the emissions, right? You're using devices, so all the heat and all will be there. So it is the duty of the person who owns the building to do all this. And then you have second as gas monitoring system. This could save us $69 billion by reducing meter reading costs and then increasing the accuracy of reading for citizens of municipal utilities and agencies. The financial benefit is obvious for users and utility companies when the utility is managed by the city. Okay, so there are very important advantages, that your safety, that your gas doesn't get leaked, and all this comes under the safety of it. And in case of consumption increase, a timely alert could be sent saying that you're using so much of gas. So it may be like you've by mistakenly turned on your gas cylinder, your gas stove, and then you have left. So when the smart device detects that so much gas is being used, so you don't leave your gas on for 1 to 2 hours and all. So it will give you an timely alert that could lead to an emergency response. So if it realizes that nobody is using the gas, and then and there is the stove is being on, so what you do is you trigger an emergency response, so which dispatches soon. So it may be like it turns it off automatically or something like that. Then you have smart parkings. This could create $41 billion of savings, so in real time. So here residents can identify and reserve the closest available space, and then you don't have any complaints. So and you can introduce a demand price. So what you're doing is you're charging for the facilities that you're providing by making it a smart parking space. Then you have water management. The smart water management could save $39 billion connecting household water meters over IP network. So your benefits is that real-time consumption, viability, and leak detection. So if there is a leakage of water, you know that you can save it by detecting the leak. Okay, and then you have a gate or a pump that can be opened and closed remotely. So you can stay at home and then turn on your motor to your house and all. And you can vary the flow of input and output by analyzing the data. So till now, whatever was explained was about general smart cities. So you can use any of those content to write and fill up pages, because this is your last semester, and then they don't always concentrate on the correct content. They see how much you've actually written. And then so going to the main question, that is over here. That is your main content. That is your smart city IoT architecture. We'll go in order. Smart city IoT architecture. So what is smart city IoT architecture? Your infrastructure is mainly 4 layered. Okay, these are the key points you need to remember about city architecture. You have your street layer, city layer, data center layer, and service layer. Okay, and then the data flows from device at the street layer to the city network. So what happens is it goes from bottom up. It goes like this. Okay, where the data is aggregated, normalized, and virtualized. The data center layer provides information to the service layer, which consists of applications that provides services to the city. So your service layer is the layer that provides the services to your city. So it uses the data center layer to get the data, and then the city layer and provide functions to the city. So what are your service layer mechanisms are your applications. These are your applications and distributors. Okay, so what happens here is you have a parking management system, you have a street lighting management system, then you have this gas security, and then you have traffic management system. Okay, so what happens is then you go to your data center layer. You use internet and other networks to connect to it, right? So what happens here is you have network management and then location sources, so that you get to know from which location or which part of the city what is happening. So you have a DC switch, a wireless router, and you have storage devices, which is virtualized. So what happens is this sends data to the internet, and then it uses internet and other networks to distribute the data and provide services. So what happens here is in the city layer, you have distribution switches, and you have different routers which are present over here, which connect us to the street layer. In street layer, you have street lights and sensing nodes. Everything street layer in general has all your sensors and nodes which are present. And then for parking space, you have sensors, and then traffic control, you have sensors. And then you have mobile devices which need your sensors to be activated so that you can connect through your phone and then give. So you have a few of the products which are there. That is, you have now your storage, and also it should happen through a set of modes, right? So using the internet to store stuff. So you use on-site clouds, partner clouds, or private clouds. So in you have this as your delivery model. So you have private clouds, so that is your information will be related only within the area, and then it makes sure that you have maximum security. On-site clouds is that you have a large shared cloud which gives you data on the area particularly, and then you can access the data related to if you have parking spaces app, and you can use the data in the app only. I mean, you can get the data of the parking spaces by only being inside the app. You cannot get it from other places. So you have transformative outcomes. That is your new government models which are implemented in cities. Then you have underlying platforms, and then cases like traffic, parking, lighting. So you use whichever platform is okay, and then you check. Then you have a IOE for third-party sensor implementation. You have new smart services for city and citizens. So city and citizens, you have new smart services which are provided. So you have a few products which are used. That is your Cisco products. Here you're using Cisco. So you have Cisco products, Cisco services, and Cisco partner. So in Cisco products, what you're doing is you use Prime MES, smart connected Wi-Fi transformational playbook, and then you have wireless ruggedized APs. Then you have IT industrial switching, routing, or gateways. So you have a lot of Cisco products which are used over here, like routers you use, and then you use gateways to transfer the data. Then you have internet connected Wi-Fi transformational. So you use the internet and network to connect through. And then you have Cisco services. These are your consulting services for smart cities. And then you have your installation and deployment solutions. So what they do is they install software so that you can work on applications where you can book data, you can check your traffic management, make sure it gives you remote access and remote availability to change data. And then you have Cisco partner, that is, it provides urban services. You have sensor solutions. So you have they work with a lot of partners which will help you give up a team. So in case you don't know how to manage, if your sensors are wrong or repaired, you have Cisco set of partners who come in to help, and then they manage your services. They give you your network operational this thing and all. So what happens in first layer? That is your street layer. Under street layer, in smart city architecture, there are mainly 4 layers. So first layer being street layer. This is where the devices and the sensors collect the data and take action based on instructions of overall solution. And give us instructions on overall solution, as well as networking components. So the sensors that collect data sources generate data required to understand the physical world sensors. So what happens is it takes a the sensor gets the data from whatever area it has. So it senses the data which is present here. It gives it to the real world so that the data can be measured and then can be detected in physical world. So what happens is you have ICT, that is your information and communication technology connectivity solutions that rely on sensors. So your information connectivity and solutions technology, that is your ICT. What happens is this relies on information. This relies on sensors to collect the information and give it to them so that the data can be properly analyzed and be used for operational use cases for the city. So the variety of sensors that can be used, there are a lot of variety of sensors which are present. So one of them being is the magnetic sensor that can detect parking events. It analyzes the heavy metal object which is present on the car or the trunk, and then when it comes on top of it, then you have light controllers that is can dim and brighten the light depending on the ambient and conditions. So if it is too dark, it can brighten the light. If it is too bright, when you don't need the light, it can dim the light. Then you have video cameras which when combined, so it detects faces and then make sure you have clear values. And then you have traffic conditions, you use cameras for detecting traffic and all. So you have air quality sensor. So you can give a few devices as your sensor examples. Then what happens in city layer? At the city layer, which is your data from your street layer goes to your city layer. So what happens in your city layer is you have a street layer. You have networks, routers and switches that must be deployed. So you have in the previous, that is your street layer, you have your sensors. So all these sensors need to send your data to something, right? So what happens is you have your switches and routers which distribute the data to whichever place that is required. Here what happens is the city layer may appear to be simple and transport layer between edge devices and the data centers of the internet. However, one key consideration of the city layer is that it needs transport multiple prototypes for multiple types of IoT applications. Now for AC you need to give the temperature type, and then for like parking space that we studied, you need the metal detector sensor type. So it'll have multiple sensor data. So it needs to use different protocols to send different types of data. So some of the applications are delay and jitter sensitivity. So now you can't send every data that you get immediately, right? So you might have a delay. So you have a delay and jitter. Some of the responses may be a little unclear. So that is what happens in delay and jitter services. So as a result, the city must be built around resilient to ensure that the packet coming from sensors and gateways are always forwarded successfully. And so you don't want any data to be blocked. If it is in a remote place and you're like when you turn on Bluetooth, if the device is very far, you can, there are instances where you miss out on data when you're listening to songs. If your phone is far away and is connected to Bluetooth, you have a lot of breakage in your songs, right? So that is what happens. You have a lot of jitter and all. So to avoid this, we should make sure that the sensors and gateways are will always forward the data successfully. So we're ensuring that it is built around resiliency to ensure that the packet is delivered properly. So here is one diagram of how the data is changed. You have your data which is given by industrial switch. You have your root APs, and then it gives you to your industrial switch. Here what happens is you give it to the edge port, and then the next you have data center layer. Ultimately data collected from the sensors is sent to the data center. So all your data is stored in your data center, right? So that is where it is sent. It is processed over there, and then it is correlated. So based on the processing of data, meaningful information and trends can be derived. Okay, so you're analyzing the data after collecting it, and then you're classifying the data as meaningful or not meaningful sentences. So you're getting the they've given an example of getting the global view of city traffic to help authorities decide if they need more or less common transport vehicles. Okay. At the same time, an automated response can be generated. You have like these default alert messages, right? So once you log in, you just give like congratulations on logging. That is all those are like your automated responses. um, so similarly, for traffic information to be processed regularly, uh, coordinate the street light duration. So now if you know your street light duration can be done based on time, right? So it can be triggered based on time. So assuming from 6 to 9 o'clock in the morning, you want your uh, street lights to work. So you're giving the trigger warning of time. So you're giving this, and then asking them to automatically generate the response. That is, it turns on and it turns off. Then you have a key technology for creating any comprehensive smart solutions with services in the cloud. So you have your data centers which can be placed on the cloud also, right? So your data exchange can happen over the cloud. You don't need a physical device to connect it. With cloud infrastructure, data is not stored in data center owned directly or indirectly by city authorities. So instead, data is stored by rented logical containers that can be accessed through the internet. Okay, so your government or city authorities don't really have access to your cloud, so they can use the logical containers which can be accessed through the internet. Okay, um, you can store in this. You can also store multiple amounts of multiple contracts can be stored and process data at the same time. So at the same time, you don't have to wait for one function to be completely over and then do it. So it is also flexible, and the proximity is maintained for exchanging of information between smart system, allows deployment and leverage for IoT systems. The cloud provides a scalable and secure, reliable data processing engine that can handle the immense amount of data passing through it. So much data is passing through it. So your cloud provides scalable and secure solutions. Mm, then you have your smart city issue. It doesn't just require efficiency to use the infrastructure, which the cloud helps. It also requires new data processing and management models. So you can't just use something that was used 20 years ago. So you need to get upgraded and then check what are the new data processing tools. So you have cloud software as a service. So that in this, this is a cloud service which is provided. So in this, what happens is you can use your software by uploading it, connecting it directly to the cloud. You don't have to deploy it as your own this thing. You can access it directly from the cloud. Then finally, we have the fourth layer, that is your service layer. So your basic your connectivity services that are measured data can be provided from different users operating within a city, right? So your different services are used by different people. And then smart city applications can provide value and add visibility. They have to provide value and add visibility for various type of users, city, like including city operators, citizens, and law enforcement. um, the collected data should be visualized, and according to the specific needs of each consumer of the data that is particularly experiencing data, it should have a individual use case. So if I am the person using it, so for me, my experience should be my experience should be unique, because for me, when I'm booking the data, if uh, someone else who has already booked the seats of a ticket counter is shown for me as available, then it'll have a lot of disturbance in the way it processes data. With different levels of granularity and scale, the same data performs three functions, or for three different users. So it has different. So along the same lines, traffic information can be used by individual drivers to find the least congested route. So you can find the least congested route, but if you're going through another route, if you're taking a new route, then your whole route will vary. Then you have a variation of same information that can be made public transport users to estimate travel times. So you're a if you're a public transport if you're commuting through public transport, and then there are a lot of people using this, so all your time and all your time, estimated time travel and all information can be made available to it is the variation is same. It's not different from others. Like if someone is traveling with you in the same bus, the time required will be similar. So public transportation systems such as buses can be rerouted if you know the congestion points. So when you see Google Maps, right, you if you have a road which is under construction, it gives you a new road, and then if there is sudden traffic unexpectedly due to accidents which happen, it reroutes for you so that you have a better road and a smoother travel experience. So then you have your number of subway trains that increase dynamically to response to increase traffic congestion. So if you have more traffic congestion, then you know you need more trains because your trains are overfilled, there are a lot of people waiting. So what you do is you anticipate the decision of thousands or even millions of commuters to take public transport, and then you may you give them a better model. Hence there are some type of data that is utilized by different types of users in different ways based on their specific needs. Smart city use cases. Here what we're doing is we are finding it out for connected street light. So what now we have a concept called smart city connected street lights. Okay, so what happens here is the street lighting comprises of one of the largest expenses in municipality utility bill. So this happens up to 40% of the total, according to New York State Department of Environment Conservation. So the maintenance of street light is an operational challenge given the large number of lights and the vast geographical distributions. You have street lights being placed everywhere, so this poses a common problem, and then it's just not just related to one area, it happens in all other areas too. So the connected street light solution, what is the street light solution now? So cities commonly look for solutions to help reduce lighting expenses at the same time by improving efficiency while minimizing the upfront investment. The installation of street light solution can provide significant energy saving and can also be leveraged to provide additional services. In regards, so LEDs, you use LEDs over here, light emitting diodes. Technology leads to transition from traditional street lights to smart lightings. The LEDs require less energies. It requires less energy than the traditional lights which were used. They have much more longer lifespan, and then maintenance cycle is also longer. You don't have to change it every 10 days. You can change it 2 years once or 3 years once. So what happens, LEDs are well suited for this smart solution use cases. So the color and intensity can be adapted to the site requirements. Like in case you want yellow color light to make sure it is bright enough, or you can give white light. It depends on the requirement of the particular place. So then you have street light architecture. Connected street lighting uses a light management application to manage the street lights remotely. So you have you get an application on your phone which through which you can monitor your street lights. So you don't have to always. So you have a management application. And then you have an application that attaches LED lights, monitors their management and maintenance. So this app will give you data and analysis of when the street lights have to be changed, when the lighting has to be made more, and then gives you remote access and allows you to view the operational status of each light. So if any of the street lights, so street light is not just one, right? It is a series of lights. So what happens is it gives you the status of each individual light also. So in most cases, a sensor gateway acts as a intermediate system between the application and the lights. So you have a sensor gateway, okay, so that the light control, so you're getting the light control nodes. The gateway relies on instructions from application to light and stores the local lights events as an application consumption. The control and LED lights use the cloud connect to the smart city infrastructure as shown. So what happens here is you have a light control node, and then you have a RF mesh. Okay, this gives you this is connected to a sensor gateway. Here it is connected to access points, which is in turn connected to an access switch. The light actuation and events happen, and then the data is sent to the cloud. In the cloud, what happens is you have a cloud layer which is connected to light actuating and events. all of these. So these are device management cloud. You have 3 device management clouds, and then you have an app which gives you the light management application, operation dashboard which controls the data, and then you have an SOS app. So if you want to turn on the lights through an application in a given area for safety and security, you can turn it on. So here what happens is a human or automated operation can use a cloud application to perform automated scheduling for lights. So you can time it between night 6 after 6 p.m. to 9 a.m. Okay, so when you turn it on, so when the clock when your digital clock which is attached to the application goes to 6 p.m., it turns on the light and then make sure it is on. So that is what is scheduling lights, and then you get the light sensors to perform the automated dimming or brightening. So you don't have to maintain. See, when you have street lights, when it gets maybe after 7 o'clock to 9 o'clock, since it's a little brighter compared to the night, what you can do is you can start dimming the process, and then maybe after 6 or 7, 6 to 7 it can be dim, and then after 7 p.m. You can make sure to brighten it. So the schedule can also impact the light intensity and the level of possible color depending on the environment conditions. Lighting nodes vary widely in the industries, especially with respect to elements and the communication and whichever protocol they use. The lighting nodes may vary. So these features are optimized for different circumstances and conditions. So no single lighting node can support all environments ideally. So you don't. So it's not like one case fits all. So you for everything, for every condition and circumstances, there are different types of lighting or protocols that needs to be followed. So you have many solutions leverage wired connectivity either by the use of existing city cable infrastructure or by adding a cable adjacent to the power cable. So you can add one more extra to the power cable, or you can give a separate wiring for only your street lights. In case the cabling was not practical, wireless technologies may be may bring interesting capabilities. You have a concept called wireless technologies which can be used. So you can turn on the lights by placing sensors over there. So you don't need which automatically trigger a response. So you don't always need wired cases. But in all cases, the built-in versatility offered by 4-layered architecture ensures that different types of technologies optimized any fit of city topologies can be incorporated as a flexible solution. So if you have a better if you are sure you need one the 4-layered architecture we had, right? The street view, the street layer. So in all those, you can incorporate these things and make sure it is a viable solution. So you have smart parking use cases. So these add these. Okay, so added to the traffic congestion which is already being present, the drivers look for parking spaces, and it has several consequences. It contributes to pollution because people they give extra carbon emissions while searching for parking spots. They cause motoristry frustrations, like where if you don't get they have a road rage, they try to drive faster to get the parking spot which is present, or maybe there's only one parking spot, so you drive from one end of the road to the other end of the road in full speed. So that causes motorist frustrations. Then you have increased traffic incidents, that is while searching for spaces you're not concentrating really on the road and can cause accidents. There is revenue loss in another consequence of drivers looking for unsuccessful parking spaces, and also has various negative side effects. The city often loses revenue as a result of inadequate parking meter enforcement, no parking and no standing. And loading zone violations, city loses its revenue. So parking administrative employee productivity suffers. So when employees are wasting time roaming on the street, the productivity of the area reduces. The parking availability after income affects income. The local shops and businesses lose customers because of decreased accessibility to the parking storage due to parking shortage. So understanding the smart connected parking, what happens here is, first you have a world sensing vehicle sensors. Okay, they have advanced node video analytics. So this uses LoRa, and then this uses Wi-Fi. So this has LoRa world sensing software, and then this uses access points and access switches. So and then it parking event happens via DC, and then other sensory vendor platforms. You have so many vendor platforms which sensory vendor platforms which are which coordinate parking events. So here smart connected devices platform. So here what happens is you have operating dashboard, end users, and then guided enforcement act. So what is the main part of this? When going on, when you see, you have parking architecture. So first what happens is you have various sensors which are available in the market to sense different occupancies. So first you have in-ground magnetic sensors. So with in-ground magnetic sensors, video based sensors which detect videos based on video computing, and radar sensors that sense the presence of vehicle due to volumetric detection. So most sensors installed in the ground must rely on battery power. So if it is installed in the ground, it must rely on battery power, and since running a cable line is very expensive. So in larger environments, a longer range, low power wide area, that is LPWA protocol is common. So you need low power wide area protocol is used because you have a large area to cover with sensors. So these parking sensors are typically event driven. So when the parking space is needed, or when it is occupied or becomes vacant, that is when the event is detected. So the sensor detects an event and identifies it based on analysis. So the communication happens through an access point. It happens through an access point through the gateway. The gateway, this is the gateway, okay. So this gateway sends the information to the cloud or the fog application where it is normalized. So this they use this platform where the data is normalized, and it goes to the application and a platform where it shows if the parking space is vacant or occupied. So what are activities that truly happen in a parking space? Once the parking space, when the driver is nearby, he can book a parking space, and then he can, out of the list, he can pre-book the parking space and then pay for it in advance. So what happens is when you've already parked the vehicle and you're not able to come back on time, you have this in-app payment mode where you can extend the time by paying the extension fees for the parking area, and which will not disturb many other users. So if the parking space is once the parking space is empty, it will show it to the other users who can use the parking space or not. But it should be relevant to the particular area which it is being used, and should be real time access. So if it uses stale or data in rest, it is of no use because I would need the parking space at that time. So the potential user experience based on 3 different types of people, that is city operators. So these are the users that want high level up map. So they want a map of the city, and then the city's ongoing parking situation. Here what happens is these are your city operators. So they give you the map. They are the ones who monitor the parking spaces which are being allocated. They would also need information on historical parking and data patterns to understand the congestion and to see where they can improve the efficiency. The parking enforcement officers, these require real-time updates on parking and charges. So if somebody leaves their car for too long, you can issue a ticket or send a warning to the citizen when the time is near expiration. So this focuses on the driving a revenue. So this main focus will be revenue. This focus will be to make planning better. Okay, so then we have citizens. The users might want an application with a map. So they want to know where the thing is showing available parking spots and reservation capabilities and online payment. Their focus would be minimizing the time to get to the. Their focus is minimizing the time. Time is the focus. Getting to the parking spot and then avoiding parking tickets. The application could warn when the parking duration is over the limit, and they can pay an extension fees, as I said before. So you have smart traffic control as your next topic. Once you finish the smart traffic control, we are almost done with the smart city architectures. So smart traffic control. Traffic is one of the most pain points of any city. So this leads to accidental death globally. So we don't want. This causes immense frustration and heavy contribution of pollution around the globe. Smart city traffic solutions would combine crowd counts and transit information, vehicle counts, and so on, and send events regarding the incident on the road and the controllers on the street, so that they could take action. So we have smart traffic control architecture. So in this architecture, if you see, you have cars and then you have a Wi-Fi which sends the data about the traffic, the vehicle counting and onboarding analytics. Okay, so this goes through a video stream or maintenance. So this goes to the cloud analytics where the API integration and then reaches a platform. This is sent to the partnered application. That is, if your Google Maps are giving you data if the road is free or not. So citizen traffic app, that is our, for example, our Google enforcement app, so that they can see where the problem is and then try reducing the congestions. And then you have traffic ops center, so that you can, if there is any accidents or any other reaction which you can take, that is done through traffic ops center. And then you have your architecture. Okay, so this is the architecture which is shown. These networks go through several architectural layers and reach the application that can drive traffic services. These services include traffic light coordination. So this include when you're traveling on Google, when you're traveling and you use Google Maps, you have this orange color line. I mean, if the road is free, it is generally blue, and then if you have light congestion, that is orange, and then if it's heavy congestion, it's red. So these orange lines include our traffic signals. So what happens is, so it is the traffic light coordination is also done. So some of the sensors can recognize abnormal patterns such as vehicle moving in the wrong direction or reversed lane. So if you have seen on Google Maps, if you take another route, like other than the route you were supposed to maintain on, if you take a new route, it redirects you to the correct route. So that is what happens in traffic management. So there are other types of sensors apart from traffic control solutions that include Bluetooth vehicle counters, real-time speed and vehicle counters. So these sensors provide real-time perspectives of offering data from historical data for correlational purposes. So you have smart traffic applications. So here what happens is the traffic applications that can be enabled to take immediate action with some other sensors to manage traffic and to reduce pain points. You're basically managing traffic, and then historical data can be used to develop a more efficient urban planning. So your common traffic pain points is stop and go, where traffic flow suddenly comes to a halt and then flows again. This wave-like pattern is a natural result of unpredictability of traffic speed ahead, and as long as it's been studied by the public and private organizations. We have a well known remedy for stop and go traffic, and it's regulate the standard flow speed based on the car density. As density increases, the car speed is forced down to avoid a wave effect. So as we studied before, you have a wave effect. That is when you're going in full speed, you have to suddenly stop. So it is constant for a while, and then it has to go down. So this is a wave structure which is being followed. So when the speed is forced down, to avoid the wave step. So if Then we have an application that measures the traffic density at in real time and can take action by regulating street light cycle duration. So if you have a lot of traffic, you can have the street lights also maintaining on the same order, thus limiting or suppressing the wave. From the driver's standpoint of view, the wait time before being able to get on the highway or the main street, the traffic on its main course is slow but is steady. If you have a steady moving traffic, it's a good sign. So the impression is that the traffic was slow but moving. So the overall result for better commute. So you don't want to be stuck in traffic and not move at all. So the main concept over here is you have to give them a route in which you have at least steady moving traffic. It goes slowly, and then you can pick up speed as and when you go, when the roads become free. You also have a topic called connected environment. Okay, so what happens here is you're using the 2017's data for to see that 50% of the world population has settled or less than 2% of the earth's surface area. Okay, so you have on 2% of earth's surface area, more than 50% has been settled. Okay, so what happens here is the dense population. I mean, if everybody is densely populated in one particular area, you have a lot of gas molecules being released due to the breathing and the carbon dioxide being produced. So more than 90% of the world's urban population breathes in air with pollutants. So the main concept of this connected environment is to give us a uh, better air quality. I mean, you're trying to find the better air quality over here. So they've given that it leads to worldwide death because they're using a lot of you're breathing air with a lot of pollutants. So you have need for connected environment. So most of why do you need it? So most cities are monitored there. So you need to monitor large cities with the air quality. The data is often driven by from enormous quality monitoring stations that are expensive and has been around for decades. These stations are highly accurate. They're very accurate, but their range is limited to a city. So if you have if you give a particular area, it'll work only in the particular area, and for another area, you need to develop another one. So it may have many blind spots or coverages. So here what happens is the price and the size of the air quality measurement stations cannot afford. So it's very expensive and huge. So you can't just go on implementing it everywhere. So it reports on a localized level. So what you're doing this is to fully address the air quality situation of a short term and long term. The smart city would have to understand the air quality hype on localized, real time, and distributed basis moments. So what happens here is so you're see, instead of getting one small area's data about the air, and in when you're having a smart city, you're trying to analyze the quality of air. So what you're doing is you have open data platforms that provide current air quality measures from the existing. So using the previous all existing data, you give your current air quality measurements for the existing air. So what is happening here is the sensors provide accuracy of the air quality stations, but they are available for much lower prices. So instead of using an expensive device, you're using a more affordable and cheaper device. So what you're using here is actionable insights and triggers to improve air quality. So the visualization of environment data for consumers and maintenance of historical data records is done over time. So what happens over here? Connected environment architecture. So what you're doing here is you're getting air quality monitor stations, cellular based sensor hub, Wi-Fi based air quality monitors, citizens wearables. So you have a lot of the amount of oxygen they're breathing in a particular area. All this can go through citizens wearables, cellular based sensor hubs. So you have a lot of you have 3G network providers and all this and all comes under cellular based hub. This happens in the street level, and under the network layer you have your 3G network providers, and you have your access switch for Wi-Fi based air quality monitors. And then here you have the data collection center. What happens here is you have your open data air quality. Here you have sensor vendor 1, sensor vendor 2, and then crowd sourcing. So you're getting this from the crowd. So what happens is you're finding the air quality and then you're giving the data to smart connected digital platform. Smart and connected digital platform, here where operators and dashboards, third party applications and heat maps can be found. So here what happens is offer offerings using so you're using variety of communication protocols. Here the connected environment sensors may measure different gases depending on the city's particular area air quality issues, and may include weather and noise sensors. So your sensors may be located in a variety of urban fixatures such as street lights, and then you have street lights, you have watches, wearables and all, which can give you extra related data. They may be embedded in the ground or other structures. So these air quality measurements can be embedded in the ground or other structures like smart city infrastructure, like how the magnetic sensors were placed underground for parking system. So even mobile sources of information can be included through connected wearables. These might choose purchase to carry with them and air quality around them at a given moment. Now, since right now we have our wearable devices such as watches calculating SpO2, right? That is your oxygen level. So you can have watches in the future which also give you the air quality which is present in a particular area. The crowdsourcing may make this information available in a global system. Communication technologies depends on the location of the sensor. So depends on the location. Now like Delhi is very polluted, and then when you come to some other place in south, you know that the pollution level is not as much as Delhi. We know that the wearables are typically communicate through short range of technologies like Bluetooth and devices nearby. That devices can in turn, so when your watches can send data, your watch can send data to your mobile phone, and your mobile phone via using Wi-Fi you can share the data on a global level. The sensors are installed in urban fixatures, also in variety of communication technologies. The sensors include street light, the same thing. They roll street lights in underground. In sensors which are located under which may be embedded in the ground can also be used. And then in additional to air quality sensors, you have wearable data, and then data center layer application that gives you details about your weather stations also. These are all data inputs that come from highly accurate sense of air quality in a city at any given moment. So as of now we have completed majority of our questions. You have questions, short notes on Raspberry Pi Model 1 and Raspberry Pi Model 2, and then you have one question on temperature sensor, that is your DS18B20, and then for safety, this is not given, this is given in the previous year question paper. So what we're doing here is we're learning two programs, one on temperature and one on blink LEDs. So we'll do the short note on Raspberry Pi model. First, let's start by understanding what is Raspberry Pi. Raspberry Pi is a series of it's a series, okay, of card-like structures. It's a card-like structure on a single board. A single board computers which developed in the United Kingdom called the Raspberry Pi Foundations. So these are several generations of Raspberry Pis that have been released till now. So it's like a credit card sized single board. Okay, so the first generation was is called as Raspberry Pi 1B model, which was followed by Raspberry Pi 0. And then you have Raspberry Pi 2, Raspberry Pi 3. The second part, that is your Raspberry Pi 2 model BG plus GPIO. So that I will write it down. So your what is your Raspberry Pi? It's a small card-like structure which runs as a computer. Okay, that's your that's the Raspberry Pi. And then what is a GPIO? If you ask, it's like a common input and output pin socket which is present. So this GPIO pinout diagram is as follows. you need to remember that there are 14 titles that you need to write if you're drawing this diagram. So firstly, you draw a rectangle and you draw four small circles. So this is a mounting hole. So there's a it's a square mounting hole, that because it's placed in a shape of a square, it's called a square mounting hole. Then you have a run header used for resetting. Run reset used to reset the pi. Then you have a Broadcom BCM 2835. Okay, what happens over here is this acts as your processor. This is the brain of your GPIO pinout diagram. Then you have a micro SD card holder. It is like a pin structure. So it's a micro SD card slot. Okay, so what happens here? Then you have your display connector. This is called DSI, display connector. Then you have a switching regulator for low power consumption option. Then you have this is your mounting hole, which I'll shade it off. Then you have a 5-volt micro USB power. Then you have a HDMI port. You have a HDMI port. This port is used for output. So it's an out port. And then you have a camera, CSI. For display it is DSI. For camera it is CSI, that is camera. Then you have a 3.5 mm audio jack. 5 mm audio jack. Then you have an Ethernet port over here to provide your internet. You have two USBs, like double USB pins over here. That is written as your into two B ports. And then you have 40 GPIO headers. Heads or headers? Headers. You don't have to really write the name of this. You just have to write it as Ethernet control. Okay, so when you count and see, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. So you have 14 things to name. So when you start, okay, first this is like your phone model. Okay, it's a small card which acts as a computer or a phone. We'll consider phone for this situation. What happens over here? A phone or we'll use a laptop. So you have an Ethernet port because you need to connect to the internet. Then you have a 2x2 USB ports so that you can add additional mouses or keyboards over here. And then when you come like this slowly, you will go in anti-clockwise direction starting from here. Then you have 3.5 mm audio jack. You can connect your earphones through your audio jack. That is the 3.5 mm pin. So you have camera access. Okay, that is your camera connector. So CSI camera connector. Then HDMI out port to put your presentations or give any other presentations through a wired network. Use your HDMI out port. Then you have 5-volt micro USB power. So this is to hold your this is your battery. So you use this port to charge your battery using a 5-volt power supply. Then you have switching regulator for low battery consumption. When it goes to ultra battery saver mode, when it's below 15%, it goes to ultra battery saver mode. So that is why this is used. Then you have DSI display configuration. So you need your display, your screen to display stuff for you. So that is your DSI. Then you have micro SD card, so that it is like it acts as a storage memory. This is your processor, that is your Broadcom PCM2835, and then you have a run header restart. Just assume that it is your power button when you click and it restarts. You have a square mounting, so this is a chip. This is all placed on a chip. So where is the chip placed? In your motherboard. Now your motherboard is connected to the base of your laptop, right? So on your laptop, the metal device, that's where you keep it. So what happens is you have small your small stand like structure on top of which you have to place this, so that the components below or the soldering below doesn't touch your laptop base. So what happens is you keep it's like a small stand. So what you do is you mount it on these four corners. That is why you have this four mounting holes. And then you have 40 GPIO headers, and then you have an Ethernet controller. 40 GPIO headers is used for input and output devices, where it can be connected, and one of them is ground volt. And then you have Ethernet controllers. You have a processor, that is your BCM 2835 SoC, that is your system on a chip. So this is your first generation Raspberry Pi. And then you have level 1 cache, that is 16 KB, and then you have level 2 cache, that is your 128 KB. Your level 2 cache is used primarily by GPU for graphics. And then you have Raspberry Pi 2, which uses a BCM 2836. It was 35 over on top, and then now it is 36 with a 900 megahertz with 32-bit quad ARM processor. So this uses this is a A53 processor with 512 KB and shared L2 cache. The power supply is your micro USB side of the unit. Recommended input current is 2 amps. So your SD card, that's your secure digital card. This does not have any locally available storage access. The working frame is stacked on the SD card, which is embedded inside the Pi. So what happens is this is general purpose input and output. GPIO is a non-specific, so you can either add inputs or outputs. Here your capabilities are GPIO is designed to be either input or output. You have normal, high, and low one. And then you have yields values that are writable or meaningful. It yields values that are writable or meaningful. And then input values of the frequency can be utilized as IRQs, that is interrupt requests. Then you have DSI display X, that is it allows you to display a series of interfaces through LCDs. And then you have an audio jack that is connectable for a stereo sound yield. And status LEDs. These give you these are the 5 status LEDs. That is OK. That is OK, SD card access, power, FDX, that is full duplex LAN, and then link. And then you have an Ethernet port that is accessible in model B and B+. Okay, you have an Ethernet port that is accessible on model B and B+. So it gives you the LAN link on the Ethernet port. The SCI it gives you the camera serial interface. That can be that is defined for mobile industry processing. Then you have HDMI, high definition multimedia interface, which gives you video and sound yield. Then you have this is the main components of this thing. So when you're writing a short note, you can write a short note on that. So we have our last theory question that we have to do. That is our DS18B20. What is DS18B20? It is a temperature sensor which has an alarm function that can be configured to give an output signal when the temperature crosses a high or low threshold. So this is a normal temperature sensor but with an alarm function which can be configured. There's a 64-bit ROM that stores the device's unique serial code. This 64-bit address shows the allows the microcontroller to receive data from its sensors. So it's like projects like weather station and home automation centers. The same is the same. The size is same for transistors, only that the data signal varies. So you have some technical specifications, that is minus 55 to 125 degrees Celsius. You have 3 volts to 5 volt as operating voltage. You have 9, 10, 11, 12 bit resolution, that is 0.5, 0.25. It's like you just square, you take 0.5, square it, cube it, to the power 4 it. And then you have 64-bit unique address, one wired communication. So draw this as the structure. You have a ground, data, and VCC. This is the bottom view, and then this is the structure. So what you do over here is you configure the Raspberry Pi. That is, you have a sudo nano. When you go to configuring the Raspberry Pi, you have a sudo nano boot configuration. You configure the text. You add dt overlay is equal to w1 gpio. Okay. At the end, if the file doesn't exist, then you reboot, and then you go to mod probe. You're probing the module, this w1 gpio. The sudo mod probe, you make it, this was GPIO, right? So you make it therm. Now under GPIO you have therm. So go there, and then you open the new function as cd system bus w1 and then devices. Then you list the devices. Then you open to 28 and then hyphen xxx cat w1 as slave. Make it as a slave architecture. Then you have 2 codes which you have to write. That is, it's the same until here. Okay, so it is A301 4B46 7 triple F 0E 10 D8, and you check if it is CRC is equal to D8. If it is yes, then it goes to the next one, and then T is equal to 32768. T is equal to